This lecture will be covering chapter 1.1 through 1.3, Atomic Theory. So, our understanding of matter and atoms have really evolved over time. And so we can go all the way back to the ancient Greece, who were the first to theorize that the world was made of matter. So first off, if we think about Aristotle and Plato, they believed that the world was made of continuously indivisible particles into ever smaller pieces. So they didn't have the concept of a smallest possible piece that we can attribute to our modern day understanding of an atom. Whereas Democritus and Leucippus believed that the world was composed of tiny indestructible particles similar to the atoms that we know to exist. So in our modern day understanding, we know that the Earth is composed of 83 naturally occurring elements. And so there are 118 presently known elements, and 90 of those elements occur naturally throughout the universe. The other, 28 of them there, are ones that we have made through research. And so the element is defined as a fundamental substance that cannot be chemically changed or broken down into anything simpler. And so we see a list down here of some of our most common elements that we're going to encounter here. And you can see that all of these elements are represented by a 1 or 2 letter symbol that we show here on the right, and then the name of each of those elements on the left. So if we're talking about aluminum, we use the symbol Al. If we're talking about boron, we have the symbol B. And so for any of these 2 letter symbols here, you're going to notice that the first letter is capitalized, the second letter is in lowercase. And so we're going to use this shorthand symbolic notation mostly when we're talking about elements. And so a lot of these names here, chlorine, Cl, so it kind of makes sense with the name of the element itself, aluminum, Al. But some of them over here, you can notice that copper is Cu. It doesn't seem like that would be kind of a logical symbol for the name iron, Fe. But these names actually come from either the Latin or the Greek origin of these individual element names. So copper would be from cuprum, so that's where the Cu comes from. All right, so throughout this semester, you're going to get used to working with these and sort of memorizing some of these individual symbols. And so if we take a look at the relative abundance of these atoms on Earth and the human body, we can see that the Earth is mostly composed of silicon, which is silicon dioxide. So that is going to be glass and the crust of sand too. So the crust of our Earth is made up of the silicon dioxide, and then we also have iron and aluminum and some of these other metals. Sodium, magnesium, calcium are going to be these metals that make up our Earth. Whereas our human body, we can see, is made mostly of carbon and oxygen and hydrogen and nitrogen, and then calcium for our bones. Okay, so we can see that these elements here, different materials are made up of different types of elements. So when we were first discovering these individual elements and what we know as atoms, it was the work in 1829 for the German chemist Johann de Bruiner, who discovered groupings of elements that behave similarly, and he called these groupings triads. So a triad is defined as a grouping of 3 elements that appear to behave similarly. So de Bruiner realized that sodium, lithium, and potassium all had a very similar appearance and also a similar sort of chemical reactivity. The same thing for strontium, calcium, and barium, bromine, chlorine, and iodine, and so on and so on. So these triads help to sort of organize these different elements that existed on Earth. So taking these ideas from de Bruiner, in 1869, the Russian chemist Dmitry Mendeleev organized all of this knowledge in regards to elements and triads into this table down here, which is going to be a forerunner for our modern periodic tables we know now. And so Mendeleev ordered all of these elements by their relative masses of their constituent particles, so we know now as the atomic weights, and he grouped them by their reactivity, which was de Bruiner's triad. So on the last side, if we saw that lithium, sodium, potassium all grouped together, we can see in Mendeleev's table here, lithium, sodium, and potassium are all grouped together. The same thing for beryllium, magnesium, and calcium. We have calcium, strontium, and barium. Okay, so so he actually didn't have beryllium and magnesium on there. Sorry about that. But we can see fluorine, bromine, and chlorine are also these in a triad. So he grouped these different elements together by their reactivity. So Mendeleev's table not only arranged all the data of the current theory that was known, but it also provided several remarkable predictions. So on Mendeleev's table, there were a couple empty spots that indicated that there were elements that should exist that were not yet discovered. And so based on Mendeleev's table, he was able to make predictions of the atomic weights of these two unknown, undiscovered elements. And so in future work, we actually saw that these two elements correspond to gallium and germanium. And so taking a look at Mendeleev's predictions to the observed properties of each of these elements, you could see that there is a remarkable similarity between the prediction and the actual true theory. And so that's the true test of the high quality theory is, can it actually describe what you know, but also make predictions for things that you don't know. So this Mendeleev's theory was a very, very high quality theory that he developed. So we now know that we have our modern periodic table of elements. And so this periodic table of elements, which is shown here, is organized in a very logical laid out fashion. There are 7 horizontal rows. Okay, so we can see 1, 2, 3, 4, 5, 6, 7. And so we can see this long bit here, that's going to be inserted into here. So what we're going to get is 2 different columns, a long 2-row or a long 2-row bit, which is this bottom portion. Then we have a moderately length 1, 2, 3, 4 row bit, and then we have our right hand side, which is a larger chunk again. Okay, so we have 7 horizontal rows, which we call periods, and then we have 18 vertical columns in this main group here. Okay, so that main group here, we're going to be excluding this, what's called the lanthanides that we put here, the intertransition metals. We're not going to include those. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we have 18 vertical columns here. So an element within a group all have similar chemical properties. So a group, remember, is going to be our vertical lines here. So lithium, sodium, potassium, rubidium, cesium, and francium, all of these guys together are all going to have a very similar chemical properties because they are all in a group. So this is similar to the triads that were laid out by de Bruijner. And so our international standard calls for numbering these groups from 1 to 18 from left to right. So the international standard we see up here on the top numbers, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 18. Whereas the US standard of numbering has numbers in capital letters. So we go 1A, 2A, then 3B, 4B, 5B, 6B, 7B. Then this grouping is 8B, 1B, and 2B. And then you can see we jump back to 3A, 4A, 5A, etc. So my takeaway message is that the US has really messed this up. Okay, so it's sort of my opinion also with the US form of measurement. So the whole world uses the metric system, but the United States chooses to use the English system where we use pounds. So everybody else has decided a very logical base 10 way to measure things, and then we have this weird system based on the length of our foot and 12 inches and 16 ounces in a pound. It's very confusing. So the US system here, I think, is quite convoluted and very confusing. So because of that, I'm not going to hold you all responsible for knowing the US system. So I would use the international system of 1 through 18. So really, there are actually 32 groups, not 18, due to these lanthanides and actinides, which are these bottom bit. Remember that these insert down here. So if we were to count all of these different groupings, there's actually 32. But these lanthanides and actinides, these guys down here, do not have numbers associated with them. So we have main groups, which are the 2 larger groups on the left and the 6 larger groups on the right, labeled A. So these 2 guys here, and then these guys here are all called the main group elements. The transition metal elements are these 10 groups here that are in the middle. And then the inner transition metals are the 14 groups shown down here on the bottom. Okay, so again, main group are the 2 on the left, and then this big block here. Transition metals are going to be here in the middle, and the inner transition metals are those bottom 2. So the elemental properties of matter. So a property is defined as any characteristic that can be used to describe or identify matter. So some of these properties could be the volume, the amount, the odor, the color, the temperature. So anything that we can observe with our senses that sort of help us to identify something is known as a property. So for example, if I'm talking about sodium chloride, which we know commonly as table salt, we can say that sodium chloride is a solid that melts at 801 degrees Celsius, dissolves in water, and undergoes a chemical reaction to give insoluble white precipitate when in contact with silver nitrate. So these are all things that I can observe with my eyes and all of my senses, my eyes, my ears, my taste, and we can observe all of these things, and every sodium chloride that you encounter are going to have these same properties. So they can be used to identify a specific substance. So we have different types of properties that we talk about, a physical property and a chemical property. So a physical property are characteristics that do not involve a change in a sample's chemical makeup. Okay, so physical properties do not involve a change in the chemical makeup. You're not changing what the thing actually is. Whereas the chemical properties are characteristics that do involve a change in a sample's chemical makeup. Okay, so I invite you guys to pause the video and make a list of some physical and chemical properties. Some things that either do not involve a change in the chemical makeup or something that does involve the change in the chemical makeup. So for example, as you're making this list, the physical properties are going to be something that doesn't change in makeup, so that would be the color or the size. Whereas the chemical properties would be the chemical reactivity or maybe the color of something when it burns. So here's a list of some of these common physical and chemical properties that hopefully you came up with. Physical properties, the temperature, the color, the melting point, the odor, the taste would be things that do not involve a change in the chemical makeup, whereas the chemical properties would be more chemical reactions, rusting, tarnishing, something like that. So these physical properties can then be broken down into 2 smaller groups that we know as intensive or extensive properties. So intensive properties are properties that do not depend on the amount of sample. So it can be used to identify a substance. So an example of that would be the color is an intensive property. So the color of a solution of iron, or if you have a chunk of iron, whether you have a 1-pound chunk or a 10-pound chunk of iron. Okay, so iron always has that dull gray color. It doesn't matter how much iron you have, it'll always have that same color. So it does not depend on the amount of sample. That would be an intensive property. Whereas an extensive property does depend on the sample size, so the amount of a substance. So for example, the mass. The mass of something depends on how much of the sample that you have. So therefore, an extensive property cannot be used to identify a substance. So I ask you guys now again to pause your video and make a list of examples of intensive versus extensive physical properties. So here's a list here of some of the intensive and extensive properties that you should have come up with. Again, an intensive property is something that does not depend on the amount of sample. So we have color, taste, melting point, density, etc. Whereas an extensive property, which is something that does depend on the amount of sample, would be more the mass, the volume, the length, the shape. So let's take a look quickly at some of the characteristics of each of the different groupings that we're going to find within our periodic table. So the first we're going to talk about is the metals. So the metals are all the materials going from the left. So hydrogen is this first guy here. Hydrogen is kind of on its own, in its own world there. So we don't include hydrogen in our metals up here in the upper left-hand corner, but all these guys here in the red. So all the way from the left, our intertransition metals, our transition metals, and then all the way over to this sort of zigzag line here that you'll get used to seeing that zigzag line. These are all considered the metals. And so all of these metals, except for mercury, are solid at room temperature. Most of these have a silvery shine. They're malleable rather than brittle, which means that you can sort of shape them into whatever shape you'd like. They can be twisted and drawn into wires without breaking, and they're typically good conductors of heat and electricity. So if we take a look at this picture down here, we can see lead, aluminum, copper, iron, silver, these typical sort of metals that you think of, shown here as our metals. The nonmetals, we include hydrogen over with the nonmetals. So that same sort of zigzag line that we have here, it's anything to the right of that zigzag line. And so these are called nonmetals. And if we take a look at their picture here, we can see that these obviously do not look like the metals that we showed in the last slide. So 11 of these 17 nonmetals are gases. One is a liquid, such as bromine. So we can see bromine, here's a liquid. And 5 of these are solids at room temperature. So we can see carbon, phosphorus, and sulfur are all there solids. So even though those are solids, they're not metals. Okay, so, none of these nonmetals are silvery in appearance. Several of them are brightly colored. And our solid nonmetals are brittle rather than malleable. So you can see these solids here can be easily broken. And they cannot be drawn into wires, and they're very poor conductors of heat and electricity. The next we get to this zigzag line that we keep talking about that separates the metals from the nonmetals. These are called our semimetals. And 7 of the 9 of these elements adjacent to the zigzag boundary, boron, silicon, germanium, arsenic, antimony, tellurium, and acetine are semimetals. And the properties are intermediate between metallic and non-metallic neighbors. So most are, for example, of our semimetals, we can see silicon here. So we can see this is our metallic silicon here, and we know that silicon can also be used to make our printed circuit boards for our computer chips. And so they have properties that are intermediate between metallic and non-metallic, or non-metallic. Most of them are silvery in appearance and are solid at room temperature. Which is more similar to our metals, but most are brittle rather than malleable, which makes it more similar to the nonmetals. They tend to be poor conductors of heat and electricity in most cases, which would again be more similar to our nonmetals. But we know that we can use silicon to make our printed circuitry board. The reason because of that is because our semimetals, such as silicon, are known as semiconductors, which mean that they are very poor conductors of electricity unless you throw a high enough voltage on them. Okay, and we'll get to voltage way later in our general chemistry course. So these are semimetals. Now going through a couple of the key groups. So the group 1A, or a group number 1, are called the alkali metals. And this consists of lithium, sodium, potassium, rubidium, and cesium. And so our alkali metals are soft silvery metals. They all react violently with water to form highly alkaline, which means highly basic, so the opposite of acidic, products. Due to the very high reactivity of these alkaline metals, they are never found in nature in their pure form. They're usually found in a mixture with salts. For example, sodium is not found as sodium solid. It's typically found as sodium chloride, which is table salt. So hydrogen, which again is our very top left here, is technically in this 1A group, an alkali group, but it is a colorless gas with completely different chemical behavior. So we typically don't consider hydrogen as an alkali metal. Okay, and this picture over here shows the very aggressive reaction of sodium when you mix it with water. Group 2A, or the group 2, is our alkaline earth metals. So don't confuse that group 1, the alkaline metals, with group 2, which is our alkaline earth metals. And so that consists of beryllium, magnesium, calcium, strontium, barium, and radium. And so these are lustrous silvery metals. They're less reactive than our alkaline metals in our group 1, but they're still highly reactive. And so they're also never found in nature in their pure state. So even though you might see magnesium stripping as it is, the reason it is not spontaneously combusting with it surrounded is that it's actually coated on the outside with magnesium oxide, which is a non-reactive coating on the outside. But if you light it on fire, you can see that it reacts very aggressively with air to form a very bright white light. The next group we'd like to focus on is the group 7A, or that would be the group 17, which is our halogens, which is fluorine, chlorine, bromine, iodine. So these are colorful, corrosive nonmetals. So bromine again, we can see here is a liquid, and it has a pretty high vapor pressure here. So you can see it's actually in an equilibrium here between gas and liquid. When you can see it has that very deep brown color to it. So they are found in nature only in combination with other metals, such as sodium. And the group name comes from the Greek word hals, which means salt. So those are our halogens. The last group I'd like to go over today is the group 8A, or that will be the group 18, which is our noble gases, such as helium, neon, argon, krypton, xenon, and radon. And so these are colorless gases with very low chemical reactivity. So helium and neon do not combine with any other element. They're just gases by themselves, whereas argon, krypton, and xenon combine with very few other elements. Okay, so they're mostly unreactive, but they can be excited here to form these really cool neon lights are formed by our noble gases. Okay, that's it for today.